move forward. All right, so you're going to be filling in some blanks here in a minute where that box is, and that box will go away when it's time. But right off the bat, just this situation. So we have this semicircular rod here that somehow we've managed to charge the upper half positive and the bottom half negative. Okay? There's surely a way to do that and join them together. And plus Q on top, minus Q on the bottom. And so what we want to do is, what's the magnitude and direction of the electric field at the center of the semicircle? So, the magnitude and direction of the electric field at the center of the semicircle, well, plus these plus charges, each one of them is doing something like this. Okay? And each one of the minus charges is doing something like that. So these are going this way, those are going that way. We're only going to draw one of each because it would get kind of tedious to look at every last one of them. So characteristically, this one also gives us a nice angle to think about. All right. Then just the factoid that the rod is L equals pi r. Well, if it were a full circle, wouldn't it be 2 pi r? So this is just half circumference. All right. So relatively simple stuff there. Now what we didn't show or state explicitly is, why is the net electric field this way? Well, basically, the x parts cancel. I'm going to go back to those other things in a minute. Because every positive nudge that way is offset by a negative nudge the other way. So by symmetry, even though this is a semicircle, the symmetry of the charge, the fields associated with each charge along the arc, they cancel each other out. For every one to the right, there's another one to the left of the same size. So they drop out. So the net effect is down. And so you have, from the top part, the part that's above the x-axis, that would be the y part of the positive field. And there would be infinitely many of those, of different sizes. And then on the bottom, there's a pull. The y part's pulling down for all of those. And so that's a representative sum, vector sum, graphical sum in that thing. So just want to kind of make sure we establish what's already written on your page, and we're not wondering if is the professor trying to trick us again. Right. So that's just setting up the picture. And so practically speaking, let's say this is a real engineering or science situation, and for some reason we actually need a charged rod, be it charged this way or all one kind of charge. There's some device that we charge up that ring and stuff goes in the semicircle. All right? We need to be able to set up and think through how the physics will work so that we can put the sensors in the right place and tell the code to do this and blah, 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 blah. All right? So even though it's a kind of a dry, classical textbook problem, I mean, every physics textbook has essentially the same set of problems. And because they are those distributions, those shapes, those whatever, show up in a lot of places. All right. Few little housekeeping chores. Charge density, at least of the upper rod, charge density, if it's going to be linear charge density, it's going to be charge per unit length. If it were area charge density, it'd be charge per unit area, et cetera, et cetera. We tend to do a lot of linear charge density for electrostatics. All right. Well, for the upper rod, okay, so just this part, that's half of the pi r, or half the length. So we went from L to half of L, because that's the upper half of the rod. So you do all your math, and it comes out as 2q per pi r. And unsurprisingly, the lower half of the rod will just be minus 2q per pi r. Two charge densities because I have two kinds of charge. One's plus, one's minus. Okay, so, and as you've seen in prior lectures and some problems, inevitably, if we're going to sum up Coulomb's law in force or electric field form, we're dealing with charge. You can't really integrate charge, but you can integrate charge per unit length. Okay, you got to bring in a dimension that the calculus can deal with, which is going to be something geometric, which is why all your calculus books say analytical geometry or something like that. All right, so nearly done with setting up the problem, all the things that you would have to go through in order to properly model, assess, compute, etc., etc. What about this thing down here? dq, well, little d, calculus-based physics, that's a differential, meaning a infinitesimally small chunk of whatever. So every little chunk of charge is going to be equivalent to the density times a chunk of length. Okay, because charge density was charge per unit length. Charge per unit length times unit length is charge. So by taking infinitesimally small, the infinitesimally small chunk of length that's associated with a little chunk of charge, we are writing the differential of charge in terms of something that can be integrated. So then we go from dx to rd theta. So let's be careful. You know, dx is going to be, you know, some little chunk here. Well, that little chunk is equal to an rd theta, but remember, that's an arc. If you remember, arc length is r theta. It's basic trig. It's going back a while. So we're doing a differential chunk of arc length. Okay? And plus, since we're dealing with angles, inevitably our integration variable is going to be theta. So anytime you have something that deals with angles, you know you got to somehow get from a linear measure to an angular measure, which is relatively simple. It's not even calculus, right? So, but it must be that way. All right. Why don't you take a moment and copy that down, and then let's see if we need to say anything about it. All right, so let's start talking about this a little bit. Hopefully, this first step of simply defining the differential for the positive y part. Well, it's going to, if it's a differential for a part, it's going to be equal to some fraction of the whole. So d sub plus dE sub plus y has to be some fraction of dE, the overall field. And in this case, the fraction, surprise, surprise, since we're dealing with angles, it's got to be a trig function, sine, cosine, tangent, something like that. And it's cosine in this case. And the reason for that is what? Well, remember the angles here. And that's what's this diagram, you might think, surely it's opposite since you're talking about what's up here maybe, okay? Or that would be the x, but the y part is adjacent to the angle theta. Hence its cosine. So again, easy. These are just super basic definitions, elementary trigonometry. But you can't forget those things if you're going to be successful in this thing called science and engineering. Gotta remember that. Now, this next part, I'm banking on you remembering Coulomb's law, or at least the definition of the electric field. Okay? KQ per R squared. But since we're dealing with differentials, we need dq, not q. We went to all that trouble above in specifying that the little dq is going to be this arc length theta thing, right? So in the next step, none of those constants change. Well, they do change in that dq becomes lambda dx. That's taken us back up to, that's why we went through that trouble there. And then in the next phase, my lambda dx becomes, or not my lambda dx, but my dx becomes an rd theta. Again, we already went over that in the previous part. And so all of that boils down to a nice integratable, with a nice little fraction of constants out in front of the thing that's going to get integrated. Easy peasy. In fact, I think that's even Calc 1 level stuff, if memory serves me well. So that would be the y part of it, or the plus y part. Well, do you expect much to be different in the minus y part of it? No. So if you'd like to, or I'm sorry, we're going to integrate this first. So why don't you take a minute and scribble that down, and then we'll talk through this. All right, so once again, relatively simple idea that if I want to find out, what the magnitude of a field is, and it's full of a bunch of little parts, I got to have the parts. That's an integral in calculus land, so I integrate the little chunks of that. Basic definition. We just figured out that dE was made out of this constant and those variables, and we're going to integrate it over a 90-degree angle, right? So could you try to impose this on the actual unit circle and integrate it over the 90-degree angle in quadrant 2 that it's in? Sure, you could. We're after the magnitude, all right? So just a 90. We need to go a 90-degree angle for that upper part, all right? So that's pretty straightforward because there's really not much to, integrating cosine theta into minus sine theta, right? So we go through all of that, and we come out with that this is that's the answer, minus k2q over pi r squared. Well, we already know graphically that E sub minus y is identical to E sub plus y. So we don't really need to go through the calculus again, because I already know it's the same. It's the other half of that magnitude. So then it means I can say they're the same, and that means that my EY, the overall EY, will just be double that. That's why it's K4Q over pi r squared. All right? Any questions on that? Should be relatively straightforward, this basic calculus trigonometry. Alrighty then.
I had a question.
All right, now let's basically extend that problem quite literally and have a left semicircle that's all plus and a right semicircle that's all minus. All right, and now we're going to do mostly the same math, but obviously the integration will be over a different angle, okay, a full pi angle. But we have particular charge values, plus 1 micro, minus 1 micro, a particular radius. And so let's get at the direction and magnitude of that thing there. So first, I just want to float that equation out there, given that we already worked this out. Is it surprising that the differential in the plus x direction will have this k cubed per pi r squared thing? It has to be k cubed per pi r squared. Given, well, the k cubed per r squared is just Coulomb's law for a field. And we found out that that pi sneaks in there from our prior analysis. And since the y direction was cosine, because it was adjacent to theta, the x direction has to be sine. That should be, we shouldn't have to go through all the same steps that we did before. Okay? And then the plus y, I think we already did that one. I'm just pulling that forward from our last one. This is just the same result as before. And then your minus x and your minus y will correspondingly have those same features. So take a moment to scribble that down. So we have those 4 equations because we have 4 directions to address. Really 2 directions, but they're split up in terms of the plus and minus part. So now, a lot to write on the blank page that follows. Let's start with this integral, which should be an unsurprising result. Then the plus y direction. Same integral, except you're dealing with a cosine as your function, varying function. And it just happens to be the case that crunching up sine theta from 0 to pi gets you a big fat 0. If you look back at the diagram, didn't we lose? We lost the symmetry that canceled in the x direction, and we gained a symmetry that cancels in the y. The net effect was downward because of an up positive down minus, and now we switch that to left right, so our symmetry switches. And so the next 2 parts are identical to the first 2, but be mindful that these go over the 2 pi range versus, or they go from pi to 2 pi. 0 to pi. in this case, we could actually integrate it in these ways. If you wanted, you could go back and integrate it from minus 3 pi over 2 to pi over 2, something else. Yes. So yes, this needed to be pi. So we go through all that trouble. You notice the y's drop out. And we can actually finish a computation here. So the sum of all of those parts ends up giving me, well, I think the same thing I had before. Wasn't it 4kq per pi r squared when it was a semicircle? Surprise, surprise. And if we plug and chug those values, so if you recall, you look back, the charges were 1 microcoulomb charge distributions and 10 centimeters or 0.1 meters. So we get 1,000,000 newtons per coulomb. Which is pretty good chunk of force per unit charge. One thing that would be good for you to ponder and perhaps put into a learning outcome essay, why does it make sense that the full circle of charge that's split between plus and minus evenly work out to have the same structure mathematically as the semicircle that's split evenly between the plus and minus charge magnitudes? Why does that make sense conceptually? Sentence or two about that. Nice example. La da da. Right? So just the key to mental development, to learning, is the ability to challenge your own understanding, which requires you to ask good questions. Good questions are better than the answers that obtain. If you have good questions, you will obtain good answers if you're persistent. So always ask why. Be a 2-year-old for the rest of your life. Why? Why? Okay. Just be careful who you annoy. All right. Any questions on this? It took us 3 pages to get to a practical answer for a bunch of symbolic manipulations, but they have their place. Also realize this, that usually what happens is you set something like this up once, because you're actually you would do this for an actual situation that you'll probably use over and over again. And then you don't have to go back and rebuild the wheel every time. You go back and steal your old code, borrow from your old designs, or somebody else on the team. And in that regard, you just need to be able to understand the mathematics, the physics, etc., which is why you take all these courses, blah, blah, blah. So sometimes you're building something new from scratch. A lot of times you're borrowing your old ideas or somebody else's and extending them a bit further. All right, a new problem. So we have this rod sticking in the ground. It's as long as it says it is, and it's got some charge density. Unsurprising that charge density is charge per unit length. I'm not going to explain that again. We're told that we want to know the field at some distance d, some position x. X equals d in this. And again, that rod is full of charges all over its surface. Therefore, every one of those distances straight line from the charge to point D, or X, is going to be a different separation distance. The R in the denominator of Coulomb's law, R squared. Again, calculus will be our friend. We'll be summing up some stuff, which is why we write this electric field differential, which shall remain unexplained because it's been explained before, all right? It has to be that way. And the key idea here is that if I'm going to have a differential on E, I've got to have a differential on Q. Okay? So the differential form of Coulomb's law versus the algebraic form. Okay? And then, since it's a right triangle sort of thing, R has to be the square root of the sum of the square of the sides of that right triangle. So the distance, we're going to have a variable function. D won't change, but Y will. The height of that triangle will keep changing all of the time. Right? And this last part here, we've done this a few times. DEX and DEY. Trick being is, in this case, X is a cosine because the X dimension is adjacent to the angle. In our last two things, it wasn't. All right, here it is. So we do that mainly just to mess with you. All right, keep you on your toes. So, as you're scribbling, I'll say stuff because this is a lot of repeat offenses. So, we already wrote this previously. Our DQ can be written as a linear thing if I know the charge density. And then we substitute in. Now it seems like, wait a minute, I went from DQ to Q. How did that work out? Well, remember that lambda is Q per L. All right? So we bring our charge comes back in, but it's a constant, so it's going to get pulled out in front of that thing there. Also, remember that R pops in there, and so now we have, instead of the square root of d squared plus y squared, that thing squared is just d squared plus y squared. It's a little algebraic maneuvering involved there. Now, in this one, we're going to swerve away from the use of the trig functions. Okay, it's a way to go. But since we have fixed lengths and whatnot, we can basically encode for the angle by paying attention to the changing y value relative to d. So we had our last discussion, we talked about what's going on here. Can you do it with lengths only? You bet you can, because that's all sine and cosine are, ratios of lengths. So it's going to be a problem where we're banking on the lengths being known quantities, easy to determine. All right? So hence we work out that cosine happens to be adjacent over hypotenuse, which means d over the square root of d squared plus y squared. This gives us an advantage because the essence of these two denominators is fundamentally the same thing. One of them is bottled up in a square root and the other one ain't. So that goes from something to the half to something to the 3/2. That, you did that a few times in Calc 1. Okay, you know, you had to mess with that, whether you were differentiating or integrating. All right, so we come down in the end to dEx, the differential, we go through all of this in order to obtain that lovely thing. Right? And the reason why I left the Coulomb constant in there is if I took K out in front and put a little d next to a big Q, that would be misleading. That would look like a differential when it's not. Little d is a distance in this case. So you got to be careful because we use a limited set of symbols in this math game. All right? So we have all that. Okay. So, if you want to take a look at that last part, basically it's the y direction and you wouldn't expect it to change, except instead of d in the top, it's going to be y in the top. So the difference is show up there. All right, moving on to the next part. So that was our work just to get the things that we're going to integrate. So take a swing at that x. And then when you're done writing the x part, the y part, slightly more challenging because of the variable that's changing. So the y part's slightly more complicated than the x part. And you actually get a difference in that one due to the nature of what we're paying attention to. So our x part has this feature, and our y part is a difference of something else and the x part, interestingly. Or something very close to the x part, rather. Another thing that would really be great to read about in a learning outcome essay is, why does it make sense that these parts are the same? Which really is, why does this persist? Just kind of connecting the math dots with the physics dots. It's a short paragraph in the making there. On one level, your learning outcomes essays are great because they're long. Okay? It's nice when they're correct and insightful, but they need to be verbose. You take a swing at being verbose, you'll learn something, inevitably. And when we get down to it, what I've done here is create a function, a vector function, from what we just obtained by means of calculus. So think about that, and we'll come back to this in a second while you're copying all that. All right, so let's think about this function of the electric field as a function of distance in this particular situation. So this is a
particular functions for this situation, not any other situation. And all we did was take the x part of the field and the y part of the field and put x hat and y hat on it, or I and j we could have done, all right? And you need to be able to notice that this is something you can do if you are dealing with vector functions. Inevitably, you have vector parts. And you can look at that and say, well, you know, this is as a function of distance, there you go, because the length of the stick isn't changing, the charge isn't changing. What's changing is d. So this is, as a function of d, it's the only variable, therefore that's what it's a function of. All right? That's trivial, but I've noticed that often in the thick of your undergraduate experience at this level, you forget about those simplicities. But you need to be able to build these things, because guess what? Now that function needs to make it into code. Because I can have all sorts, I can have charge sensors, we have some, we'll mess with them eventually. Little sticks will measure charge. So this situation could have a charge sensor at one or more locations to know what the charge is. Or some other way that you know what charge got put on the stick. Right? You could measure the distance that something is just by a rangefinder. We did that in first semester. If we can do it in physics class with a $60 sensor, I guarantee you NASA, Sandia Lab, Intel, you know, they'll buy you a sensor. You figure it out. And this could all be computed. And then inevitably, if that rod's moving, which would be the only reason D would change, then there's motor control or some sort of control function that's based on these outputs. So all of this feeds into, you know, some sort of real life application. All right, finally, last page. Let's do something with that function that we just built. What's the electric field when V equals 5 centimeters and there's a 10 nanocoulomb charge on that rod that's 55 centimeters long? So we have the function we just built. And we plug in Chugsville. That's the beauty. If this were in code, obviously Coulomb's constant would just be a constant in the code, but Q would be something that came from another sensor input or a control action that's guaranteed to produce the same thing every time. Or maybe you don't need to, you know, and that's a constant too, the way this thing is set up. Okay? And then it's algebra. You know, physics was done a long time ago. This is really, at this point, an algebra problem. So I'll let you copy it, and then we'll do a quick assessment of that final answer and why the second component. All right. So this answer down here, we have a very large x component of the field and a very small y component of the field. If you were to do the magnitude, if you were to square those two things, add them and square root it, it would still be 3259.3. All that 13.4 does is change the 100th place, which I'm not showing on here. And so in what context would that matter? I don't know, depends on what you're doing. You're dealing with things that have insanely small tolerances, then it'll matter. If you're not, then it won't matter a bit. But if D changes, you're guaranteed. There's a length of rod and or size of the position where x equals D where that's not so one-sided in its application. So didn't bother to compute the magnitude on the screen here, but that's all she wrote for this part of the game.